Hello, this is Group 14. I'm Hewitt, and my group members are Thomas, Ann, and Sunder. This is our final project for CSI 5551 Spring 2024. Our project is using SLAM navigation on an autonomous rescue drone to find hikers. The main goal of this project is to locate the position of lost hikers, represented by indicating markers, in variable terrain in the absence of GPS using EKF SLAM. We are using a gazebo environment with a drone running ROS2. We are primarily comparing two different types of terrains provided by the gazebo repository. The rescue markers, or lost hikers, are represented by red markers, as seen in the picture. These rescue markers are randomly distributed throughout the terrain or the map. The drone in the simulation flies over the terrain with an RGBD camera pointing downwards. This allows it to get image data along with depth data. The drone also gets data from its IMU, which can give it positional data based on its heading, acceleration, and movement. GPS is used here for ground truth comparison. Based on its initial flyover, it will be able to map the terrain and produce a robot position relative to the map. It will also be using OpenCV to detect the marker position. Moving on to the demonstration video, you will see that the drone performs localization and mapping using EKF SLAM with orb for visual feature extraction. In this view, we are running the simulation in gazebo on the desert map. On the left side, you will see the live view of our drone flying across the map in its initial zigzag search pattern. On the right side, you will see data recorded and processed by the sensors. The top right view is what the camera sees. Landmarks that are tracked by the algorithm are circled in bright green. Switching over to the CV view, we can see the marker get detected with an estimated position. The desert environment with a low altitude scan was our ideal test case. On the right, the estimated marker location is plotted in blue. The actual marker location is plotted in green. The table displays the raw numeric data and error values. On the left, you can see the ground truth GPS path over time, outlined in blue. The red outline represents the SLAM estimated location over time. The IMU's estimated location over time is plotted in green. As you can see, there is some variance in the SLAM data, but it stays relatively bounded to the ground truth. Note that the starting location is the bottom left corner of the square. You can see that the IMU's error accumulates over time. This results in the IMU becoming significantly less accurate over time when compared to SLAM. Moving on, we are simulating a mountainous environment. You may observe the EKF SLAM working with the same interface as before. Notable landmarks such as rock edges are tracked in green. Here, the drone makes a pass over markers, estimating their positions based off of camera data and SLAM positional estimates. Due to the mountainous terrain, the drone had a higher surveying height. Looking at the SLAM position estimation accuracy, it seems like the mountainous terrain results in a higher rate of error. Additionally, it seems like the mountainous terrain causes a greater amount of error when estimating marker positions. One of the potential causes of errors is pitching due to acceleration or changing directions. This would tilt the camera and potentially affect the accuracy of the readings. We tested a significantly higher surveying height, and the results seem to show that height amplifies pitch error. Overall, even when maintaining similar heights, mountainous terrain seemed to have a higher error rate. The results from the desert terrain at low altitudes seems to suggest that EKF may be a viable option when GPS is unreliable. Thank you for listening to our presentation about using EKF SLAM for rescue drone navigation.